These are the notes about reaction types. Reaction types are the language we use in chemistry to describe a reaction. They don't always have a very deep meaning, but they represent a generic formula for a reaction like the ones you see here. I'm also going to show you the toy versions. Whether that helps or not, we'll see. But a lot of times, metaphors are used to describe these reaction types, and I'll be using those as well. The 5 types of chemical reaction are combustion reactions, synthesis reactions, decomposition reactions, displacement reactions, and double displacement. Synthesis and decomposition are kind of a pair of opposites. And then displacement and double displacement kind of go together as well. They are sometimes referred to as replacement and double replacement because they are that as well. The number one reaction type that supersedes the others is combustion. Combustion is a special category reserved for one particular element that is incredibly abundant and incredibly reactive. That element is oxygen. Oxygen, which of course is written in a chemical formula as O2, like you see right there, is involved in every combustion reaction. In fact, any reaction where you react something with oxygen is a combustion reaction. So as long as there's O2 on the left-hand side, on the reactant side, like as we see right here in the middle one, and down here on the bottom, okay, is a combustion reaction, this one. So combustion could be with something organic, most often it is, or something inorganic. Remember, organic chemicals contain carbon. So classic combustion, the one in the middle, we'll talk about that one first, is a reaction with a carbon-based chemical, an organic chemical. In this case, methane, right there, CH4. That's your ultimate form of combustion, the kind that I would expect you to picture as the stereotype of combustion. And then there's lots of other organic chemicals that can burn, but they usually make the same two products, carbon dioxide and water. That's what it's known for. However, not all combustion reactions produce carbon dioxide and water. Sometimes they don't even involve carbon when it's an inorganic material, like let's say a metal, like magnesium, as shown in the bottom. Well, magnesium can't produce carbon dioxide, can't produce water, so you get a totally different kind of product. I'll show you examples of both of these. So combustion is a reaction with oxygen. Classic combustion is when there's an organic chemical over here on the left, like CH4, methane, reacting with oxygen, of course, producing carbon dioxide and water. As you can see, this is not balanced. So of course we need to balance it, and when we balance it, we wind up with this equation. There's a separate notes about balancing, of course. So notice that the carbon winds up in the carbon dioxide. Okay, the carbon, which started in the methane, winds up in carbon dioxide. Well, that's way better off because now it's got 2 double bonds to oxygen. That's much more stable. Oxygen is also better off here in both situations because it's gone from these oxygen molecules, there's 2 right there, to water molecules where it can sort of beat up on hydrogen, dominate hydrogen, or these 2, let's say, went to the carbon dioxide where they can sort of dominate carbon. So pretty much everybody is better off on the product side, and of course the hydrogen, even though they're being dominated in the water molecule, it's a better situation for them, a more stable situation. So these 4 hydrogen, everything is on the right-hand side, of course. That's balancing, that's the conservation of mass. So everything on the right is more stable than everything on the left. That's why this reaction is a very easy one to get started, but just a little bit of a spark, you can get this going. If there's methane present and oxygen present, just light a match and whoosh, like on a stovetop. This is basically the reaction on a stovetop or on a Bunsen burner in a chemistry lab. However, you can have combustion without organic chemicals. Look at magnesium. Magnesium is an alkaline earth metal. In fact, this was one of the demos I did in the reaction types lab. Magnesium reacting with oxygen. This is burning the magnesium ribbon. I held it over the stove until it lit, and then it was one of the brightest reactions in chemistry, brighter than the sun, depending on your distance. This reaction produces magnesium oxide. Now that, of course, is not balanced either, so we have to balance it. And then once we balance it, of course, you can see that these two magnesium went right here, and these two oxygen atoms went right there. So everything is the same on both sides. It's balanced. Okay, don't forget about balancing. So, but of course, there's no carbon dioxide made. There's no water made because you need carbon and hydrogen to make those chemicals, and magnesium doesn't have that. So combustion is a reaction with oxygen, period. It can be a fast reaction like this one. It can be a slow reaction like rusting, or it could be respiration. We're breathing, reacting with oxygen in our lungs. We are internal combustion engines in a sense. So combustion is the #1 reaction above all the others, superseding the others. Then if it's not combustion, well then maybe it might be one of the other 4. Here are 2 examples of a generic combustion equation. The first one has a chemical, generic chemical A, reacting with oxygen, producing a compound with oxygen. Another example, the bottom one, has a compound reacting with oxygen, producing 2 compounds, both containing oxygen. That is more typical. That's what we usually wind up seeing, something like that. Those are both forms of combustion. So when we talk about reactions with oxygen, we just call them combustion. The next type of reaction is called synthesis. When you synthesize something, you're putting it together. You're taking parts, putting them together into a whole. So in synthesis, you wind up with one reactant plus another reactant producing only one product. One product. So the toy version below shows a little Pichu eating something, growing bigger. It might not follow the rules of Pokemon, but it's A plus B produces compound AB. Another very simplistic example is shown in the middle of this slide. If you see the Na ions plus the chloride ions, if they came together forming sodium chloride, a compound. Now that isn't exactly how it happens, but let's just slide over that right now. So synthesis, really the way to identify it, which is pretty easy, as long as it's not combustion, it makes one product. One product. That's how you identify it. Boom. Then we have the opposite of synthesis. The opposite of synthesis is decomposition. Decomposition is when you take one chemical and break it into parts. For example, you could have one reactant and then one product and another product. You could have compound AB breaking into A plus B. Compound ABC breaking into A plus B plus C, or other variations where they're getting smaller. Okay, the toy version of this is starting with an unhatched egg. Well, something's inside that egg. After it hatches, you've got the eggshell plus the squirtle that was inside. So that's 2 things coming out of one. So this is one reactant. That's the giveaway for decomposition. Pretty much always, if you start off with only one reactant, it's got to be decomposition. It can't even be combustion. It's just not possible. Think about it. So decomposition is another easy one to identify. It's probably the second easiest reaction type to identify after combustion. So decomposition you could break into two, but you could break into more. Okay, so there's a few different examples. Well, the toy example on the bottom is C3PO. I took my child's toy, a C3PO. It just turns out he was designed to break into his parts, the O, the P, and the C3. An example of this from chemistry, a real example, is the electrolysis of water. If you start off with water, that's one reactant. And if you break it into its parts, well, that's decomposition. Another one is if you start off with calcium carbonate, another very common chemical, and you break it into parts, well, that's got to be decomposition. If you start with one reactant and break it into parts, that's decomposition. Electrolysis is a great example. Electrolysis is really the reaction that kick-started chemistry as a real science. Because until then, people believed that water was an element, one of the 4 or maybe 5 elements that made up everything. But when they proved that water was made up of even smaller parts using electrolysis, then people had to cave. They had to say, well, wait, we were wrong. And then it opened up the science of chemistry and all the things it has discovered since. So water is a tough molecule. If you want to break apart water, you need to put in quite a bit of energy to do it. But if you have an electrical current, it can provide that energy. So basically, electrolysis of water is when you zap a water molecule and wind up ripping it into its 2 constituent elements, hydrogen and oxygen. Okay, obviously this is not the balanced version. So let's look at the balanced version, and you can see that it takes 2 water molecules to make 2 hydrogen molecules and 1 oxygen. You can see that the 2 oxygen atoms went into the oxygen molecule. These 2 hydrogen atoms went into this hydrogen molecule, and the other 2 went into this one. Okay. However, this costs a lot of energy. To do this, putting them in that form, it takes quite a lot of energy to do it. Okay, it's a very endothermic reaction. It absorbs a lot of energy. Usually you're providing it with electricity, so you're not that worried about it. And then, of course, this reaction is completely reversible, very easily reversible. Okay, so electrolysis is a great example of decomposition because there's one reactant. That's the giveaway. Now notice I want to point out that even though there is oxygen in this reaction, it is definitely not combustion. So why is this not combustion? Because oxygen is on the wrong side. Oxygen is on the right, on the product side. It is clearly not a reactant. So for combustion, oxygen needs to be a reactant on the left side. Another decomposition reaction happens beneath our feet all the time. Calcium carbonate, which is a common ingredient in many rocks like limestone. Calcium carbonate will actually break into parts. It'll break into calcium oxide or quicklime, this one here, and carbon dioxide. Well, as you know, you should know something about carbon dioxide. Where does the carbon dioxide go? Think about it. The carbon dioxide that is produced from this reaction is going to go into the atmosphere. So if you have a rock and it loses carbon dioxide to the atmosphere, there's a smaller amount left. And this is one reason why you get subsidence and sinkholes and potholes. The reason that the ground sinks down is often because of this reaction. Before we get to the last 2 kinds of chemical reactions, we have to talk about the activity series. The activity series ranks cations, basically metals and hydrogen, in order of reactivity. So basically, the one on the top wins, the one on the bottom loses. you can see on the left, I have an activity series of commonly occurring elements. As you go downward, they get less and less reactive. We pass hydrogen, and then what's below hydrogen are called the noble metals. Those are the original nobles on the periodic table, the metals that didn't seem to react much, so the alchemists describe them as noble, as opposed to all those other metals, those regular metals that were the base metals. And base metals, of course, react with acids. On the right side, you can see a fuller activity series that I've made using even really rare elements, even some that theoretically you could never actually have in a reaction, but just to show where they would fall. And we start up with francium. If you notice, francium is really the bottom left-hand corner of the periodic table. And then if you go above francium, you've got cesium. Then above that, rubidium, potassium, sodium, and lithium. Those are actually the alkali metals from the bottom to the top. They are the top of the activity series. They are above everything else. But then following the alkali metals are their neighbors, the alkaline earth metals, which are no slouches either. And you've got radium, barium, strontium, calcium, magnesium, okay, and beryllium. So those are the alkaline earth metals. So really the easy way to remember the activity series, the order it goes, is think the alkali metals are on the top. Look on the left side, you can see that again. The alkali metals, potassium, sodium, lithium. Then you've got calcium, magnesium. Okay, those are alkaline earth metals. I have an exception to the way the activity series is shown in the Holt chemistry textbook. Look here where they have these three written. They have potassium, calcium, and sodium written like that. And it says, well, they react with cold water. Well, that's true. But when sodium reacts with cold water, it basically melts and explodes. When calcium reacts with cold water, yeah, it eventually, dissolves. It changes color, changes the indicator color. So really, I think what they should do is very clearly change the positioning there, put the calcium below the sodium. There's no doubt. I think maybe they just figured, well, they all react with water, let's just throw them in a group. But the rest of the activity series in the book is okay. So below that, okay, it's pretty much accurate. So if you have a fight between two elements and you want to know who's going to win, then consult your activity series. By the way, these are all cations. So what are they fighting over? What does a cation really need? Well, a cation needs an anion. So what they're fighting over is an anion. And if you think of a lot of chemical reactions this way, they're a lot easier to understand. Two cations in a fight over the same anion. This brings us to displacement. A displacement reaction is when a single element reacts with a compound and it displaces one of the members of the compound from the compound. So usually it's a metal, usually it comes along and it bumps something out of a compound. The toy version, so it's A plus BC produces AC plus B. The toy version is this one. You can imagine that this here Wookiee is a lot more active than this goldenrod right there. So when it comes along and if it wants the prize, which here would be the astromech droid, would be the prize, well, it's going to take it for sure. And then, well, what happens to the goldenrod? Well, the goldenrod gets bumped out of the compound. It gets left out on its own, displaced. You could also say that the Wookiee has replaced it in the compound. That's why this is sometimes called a replacement reaction, because yeah, if you have one, you have the other. So there's a common displacement reaction shown at the bottom. You've got zinc coming along and fighting against hydrogen. What are they fighting over? They're fighting over the prize. They're fighting over the anion, which is the chloride. Well, who wins? Well, it turns out zinc is significantly more active than hydrogen, so zinc gets the chloride, and then the hydrogen gets displaced, bumped out. So when you see a displacement reaction, well, then on the left-hand side, you've got to have a compound and a single element on its own. And on the product side, you've got to have a different compound and a single element on its own. That's the way to recognize a displacement reaction. The great thing about these reactions is they are entirely predictable. So here is a reaction where we have copper chloride reacting with aluminum. I'm actually doing this one right now as a demo, and I'm taking pictures of it to show you. Copper chloride reacts with aluminum. So this blue solution that you see, the blue solution inside the beaker, is a copper chloride aqueous solution. Then we put in a little chunk of aluminum foil right there, floating in there, and the aluminum is fighting with the copper over the prize. Again, the prize is the chloride in this case. Well, aluminum is way more active than copper, so it gets the prize, and you get aluminum chloride as the product. So what happens to the copper? It gets left out in the cold. It gets displaced. This is the copper down here. This is the copper forming on the bottom there. Copper is like all over the place here. Copper is forming all over this. And the aluminum is forming a compound with the chloride. That's a great example of a displacement reaction. This demo is a little bit slow, so I might perform it for you in the classroom, get it started one day, and then you could look at it the next day and the next week, and you could see how it progresses. This is a slower demo, not as dramatic as the thermite or the potassium demo, things like that. So the aluminum plus copper chloride, the one we were just talking about, okay, involves a pure element, aluminum, coming along, fighting against copper for the anions that it has. Well, of course, as we already said, aluminum wins. But look, aluminum actually needs 3 chlorides because aluminum has a positive 3 charge on its cation. So it needs even more chlorides. So clearly this is not a balanced equation. And then you could say copper gets left out in the cold, displaced. When we balance this equation, it's a lot easier to see where everything went. So these two aluminum, they both got what they wanted. They won the prizes, and there they are in the aluminum chlorides. But we needed 3 copper chlorides to provide enough chlorine for these two. And then, let's see, this one goes there. This one goes there. And these two go here. Okay, to provide enough chloride, we actually need 3 of the copper chlorides, which is why we have 1, 2, 3 copper atoms involved as well in order to balance it out. So we are now obeying the law of conservation of mass, and you can see where everything came from and where it went. But essentially what's happening here is a more active metal is beating up on a less active metal. Copper is actually not a very active metal. It's below hydrogen. It's actually what is considered a noble metal, just barely considered a noble metal. If you want to determine if a reaction is going to happen, you can determine it by looking at the reactants. Magnesium is added to a solution of lead nitrate. Will a reaction happen? To understand this, what we have to do is look at where they fall in the activity series. What I mean by that is look at where the cations fall. The cations involved are magnesium, the metal, and lead. Magnesium is the most common metal in the universe. And where does magnesium fall in the activity series? Right there. Where does the lead fall? Down there, just barely above hydrogen. Notice that lead on the periodic table is Pb for plumbum, that's the Latin name, because they used to use lead in plumbing. So the word plumbing means leading. The word plumber means leader, kind of. Okay. So magnesium, there's no doubt, look where it is, way up there, easily beats lead in a fight. Easily beats it in a fight, no problem, okay? Magnesium is more active than lead. But what does the magnesium want? Well, if you look at the compound, the lead nitrate, you can see that lead is attached to NO3. Well, it actually has two of them. That's why it's in parentheses with the 2. But the nitrate, that's the prize. That's the anion. So who's going to get it? Magnesium. And then you wind up with magnesium nitrate. Magnesium also wants 2 of the nitrates because it has a positive 2 charge. Lead, of course, is displaced, left out on its own, which could be hazardous because lead is toxic to the human brain. If we look at the full activity series, well, that changes things a little, but you can still see maybe there's magnesium right there. It lines up with the word magnesium on here. And then lead is actually even further down on this one down here. Below hydrogen, of course, lie what we call the noble metals, the metals that don't react, okay, with acid. Double displacement is the last kind of chemical reaction. Double displacement is also predictable. However, it's a little more complicated because now we're not only concerned with the activity of the cation, we're also concerned with how desirable the anion is. Because in this case, now we're going to have 2 of each, 2 cations and 2 anions. So in a double displacement reaction, the parts of 2 compounds switch places to form 2 new compounds. So these are fairly easy to recognize because you've got 2 compounds going in and 2 compounds coming out. The generic formula is AB plus CD produces AD plus CB, but the toy version, these 2 guys, Apollo and Adama with their various hats on, and then afterwards you've got them with each other's hats on. They've switched hats. That's a typical way of describing double displacement. Think of the hat as the cation. Another way to describe this is when 2 couples are dancing and then they both switch partners. That is double displacement. So we'll look at a few examples of double displacement. One example is silver nitrate plus sodium chloride. So now notice we've got cations. I'll circle them in red. We've got cations, the metals. Think of the metals as the cations. But then we've also got anions. I guess I'll circle them in purple. We've got anions. So the anion in the first one is the nitrate. The anion in the second one is the chloride. So it's kind of hard to say which anion is better. Which one would you prefer? Well, there's an easy way to tell because looking at sodium and silver, between those 2 cations, who's going to win? It should be very, very obvious that silver is a noble metal. Sodium is an alkali metal. They couldn't be much further apart. Sodium is one of the most active of all of the metals. Silver is one of the least active. So sodium wins. Sodium decidedly gets what it wants. So look at the right side. What did the sodium want? The sodium turned out to want the nitrates. Sodium wanted the nitrates. So that means nitrate is a better anion than the chloride. So when sodium bailed on the chloride, separated from it, in order to steal the nitrate, well, that displaced the chloride. It got bumped loose. It got knocked out. And then by stealing the nitrate from the silver, well, the silver got kicked out as well. Where did they wind up? Well, they wound up in another compound. Those are the leftovers. So basically, the driving force behind this reaction was the sodium getting what it wants, which was the nitrate, making the sodium nitrate. In the process, displacing the 2 other cations and anions and having them form sort of the leftovers. These are like the leftovers. They have both been displaced. That is why it is called double displacement. And then what about balancing this reaction? Maybe we should balance this one. Let's see. How many silver over here? One silver, argentum, one silver over here. How many nitrates? Think about nitrate as a unit over here. 1. How many nitrates over here? 1. How many sodium here? 1. Sodium over here? 1. Chlorides, 1. Chlorides, 1. Oh, actually, look. Do you notice? This is one of those reactions. It's actually very common where you don't really need coefficients. You don't need to do anything to balance it because all of the coefficients are 1. So what you want to do is leave it alone. Don't mess with it. Maybe just put a little check over the yield sign to show that you've noticed that it's balanced. Definitely don't tamper with an equation that is already balanced with coefficients of 1, which of course we don't write. They're invisible ones. In a double displacement reaction, two compounds in aqueous solution appear to exchange ions and form two new compounds. One of the products must be a solid precipitate, a gas, or a molecular compound such as water. Well, here's the problem. If a molecular compound such as water is formed in an aqueous solution, it's not very noticeable because you've already got other water molecules present other than the ones you're producing from the reaction. So a lot of times what we see from these reactions, what we notice are the solid precipitates, What does the word precipitate mean? It means to throw down. A precipitate is something that is thrown down to the bottom of the beaker in this case. Usually it's a solid, just like when we say it's precipitating. The clouds are throwing down rain at us. Okay? Another thing that can be produced as a gas, but lots of reactions produce gas. Here's a good reaction on the bottom. This is a classic chemical reaction, one of the most classic. And we've got sodium fighting against hydrogen. Well, who's going to win? Sodium. So what does the sodium want? You can tell by looking at the products what the sodium wanted. The sodium wanted the chloride. Look over here, sodium chloride. So by bailing on the hydroxide, the OH, and knocking the hydrogen off the chloride, well, those got bumped and those wound up together in the compound HOH. Now, does that look familiar? HOH. There's another way to write it, of course. It's got 2 hydrogen and 1 oxygen. Well, you could write that H2O. But this is the way that organic chemists like to write water, because a lot of times that's the way that water forms from a reaction like this. This is a classic acid-base reaction. Hydrochloric acid, classic acid. Sodium hydroxide, classic base. And these are the kind of the products you get from an acid-base reaction. We'll talk about that later on. So double displacement is when the cation from one compound winds up with the anion from another, and vice versa. They switch partners. Here's one more example showing what a solid precipitate might look like. We've got potassium fighting against lead. Who's going to win? I mean, you know by now, I hope. Potassium is at the very top of the activity series of commonly occurring elements. Potassium gets what it wants, but what does the potassium want? Does the potassium want the chromate or does it want the nitrate? We'll look at the products. Clearly, the potassium wanted the nitrate. So the potassium takes the nitrate, which displaces the lead from the nitrate, and it bails on the chromate, leaving that behind, and then you wind up with lead chromate getting together from the leftovers. The lead goes there, the chromate goes there. But it's really, this is what's driving it. It's really the potassium taking the nitrate that is driving this reaction. So the potassium nitrate turns out to be a clear chemical in solution. But lead chromate, on the other hand, like a lot of chemicals containing chromium, are very colorful. That's what chromium means, colorful. So lead chromate is this yellow stuff you see in here. Now you might think that that's a liquid, but actually it's a solid. And if you wait long enough, it begins to precipitate, it begins to fall down, down, down to the bottom until it's down on the bottom of your beaker. That's why they call it a solid precipitate. So if you see a solid precipitate, the chances are most likely it was a double displacement reaction. That is what they are known for. That's their signature. So the 5 types of chemical reaction: combustion, a reaction with oxygen, always with oxygen, a specific element. Notice that was the only one that had a specific element involved. Well, if it's not combustion, then look at the others. One product, synthesis. One reactant, decomposition. Okay? If you get something coming along and bumping something out into the cold, bumping it out into the cold, that is displacement. If both things get bumped, in other words, if you switch hats, if the hats get switched, well, that's double displacement, where the cation winds up with the opposite anion, and vice versa. So remember, these are the generic formulas for the various reaction types. And you can't get too deep with this. This is just sort of the language we use. We could say, well, this combusted, this decomposed, this was displaced. But on a deeper level, well, there's more going on that we'll talk about at the end of the course. But for now, you just need to know the words we use in chemistry. This is certainly not one of the harder things in chemistry. You just have to be able to distinguish between these 5 reaction types. And here we can see actual examples of each of the reaction types, some common examples of each, some of which I covered in the notes, and some of which we saw in the reaction types lab. You can come back to this one if you need an example to look at, okay? But these are very, very typical examples of these reactions. Don't forget that for every chemical equation, we always have to obey the law, the conservation of mass law. We have to balance every chemical equation. When we balance equations, the only thing we can change, of course, is the coefficient. And there's a separate notes about balancing equations. Remember that we can't tamper with the chemical itself, which includes the subscripts. We can't mess with those when we're balancing.